We're going to look at an introduction to image processing with the 2D Fourier transform. And here's an image that I took on my recent holiday, and I'm showing the sampled version where we've kept one in every two rows and columns. So I've padded it so that it shows a black region, so that it highlights the fact that it started out as being 600 by 600, and now we only have 300 by 300. And I'm showing it with the black region there to highlight how much smaller it is. And if we wanted to store this image, then we could store the sampled version, and we would only need to store 300 by 300 pixels instead of 600 by 600. But of course, we've lost some information. So let's look at how much we've lost, and then how do we recover an original image. And this is a really two-dimensional version of the one-dimensional decimation and interpolation. And there's a couple of videos on the channel on interpolation and decimation, and I encourage you to look at them in the link below. So now I'm showing the first step in recovering the image, where we've taken the 300 by 300 and we've put zeros in between each, so rows of zeros and columns of zeros in between each of the 300 by 300 rows and columns to get back an image which is now 600 by 600. Okay, so just to repeat the steps, we took our original image, we only kept every second row and every second column so that we had a compressed image, which means we have less storage. And now we'd like to recover a version of the original image. We're not necessarily going to get exactly the original image back because, don't forget, we threw away every second column and every second row. So the first step is to do put the zeros in, the rows and columns, and then the second step is to filter this zero padded image and reconstruct it. And that's what we get on the right-hand side here. And you can see that there's various artifacts. It's not exactly the same as the original image. And of course, that's to be expected because we threw away every second row and every second column, as I said. You can see from the flagpole here, there's some vertical artifacts in the image and around the windows as well. So let's really try to understand what's happened here and look in the frequency domain. Okay, so here we have underneath, let's explain each of these. So here's the original image, and underneath it is the Fourier transform of that image, a 2D Fourier transform. And I can rotate it around, and you can see there are components here. There's a big DC component, and there's all of these other components. Now what we've done underneath the sampled image is I've shown that, the Fourier transform of the 300 by 300. Notice that it's only 300 by 300. Okay, so this is the sampled version of this image here in the frequency domain. So we've done the sampling, and then we've done a Fourier transform to get this image here. Okay, now when we do the zero padding of the columns and rows for this third image, then we take the Fourier transform of that, but then we see all of these copies of the Fourier transform. And you can see these copies here. This is again 600 by 600 because this image here, the zero padded image, is 600 by 600. But you see all of these copies. And to understand these copies more, again, I really encourage you to look at the decimation and interpolation videos on the channel in the link below, which explains the one-dimensional case, and this is a natural two-dimension extension. And what I'm showing here on the right-hand side is the low-pass filter that we need to apply to the zero padded image. So in the Fourier domain, we take this filter that we've padded, and to get a reconstructed image, we have to filter out all of these copies. So all of the copies that here are around the edges of this image, we need to filter them out. So if I rotate this around and look on the top, we've got copies along the outside corners and edges of this Fourier transform, and then the filter we need to apply is going to pass all of the portion of this reconstructed image that's inside the yellow area, and it's going to block and set to zero all of the portion outside. So it's an ideal low pass filter. Okay, and if you do that, you get rid of these copies and you get this image here. Now I'll just point out that you could do something else. So instead of if you wanted to compress it, so here we've compressed it by getting rid of every second row and every second column. And that has compress the image. Something else we could do is we could take directly the Fourier transform, two-dimensional Fourier transform of our original image to get the Fourier transform down here in the bottom left, and we could immediately then multiply that by this filter, which is on the bottom right-hand side. And that would remove all of the parts from the original image that are in this outer region. What that means is all of the high frequency parts. And that would be all of these components here. So here I've plotted the components of this Fourier transform, which would be removed if you applied this filter directly to it. And don't forget, filtering in the image domain is a convolution, and in the frequency domain, it's a multiplication, because convolution in one domain is multiplication in the other. So here I would show what you would be removing if you directly applied this filter to the two-dimensional Fourier transform of the image and you didn't do the decimation. So if you did that, then you could get an image, and here's what the image looks like. And so this is just another way. I mean, if you did that, all you would need to store then is the portion of this which is in the center square. So again, you would be only needing to store 300 by 300, because this one here goes from, this is 300 along this direction, 300 along here. So this is another way, a different way of only having to store something which is 300 by 300. So the first way was to remove every second column and every second row in the image domain. The second way is to take a Fourier transform, multiply it by a low-pass filter, and then you only need to store what is got through that filter, and that would be the same number of elements. Okay, so it's just a different way of doing the compression. And if you did it this way, you get this image here. Now, this image doesn't look very much different to this image. You can see certain differences. There's still these artifacts from the flagpole, but they're a little bit different. This one goes up into the clouds a bit more. You can't quite see the artifacts up there, and then slight differences. We're going to see these differences much more as we step through this video. Okay, so let's have a look at what happens. Now that we understand what all the plots are, I'm going to now sort of more quickly step through a whole lot of a sequence of more and more compression. Okay, so here's the situation when instead of doing every second row, we're now going to be removing more rows and columns. And here we're only going to keep 1 in 4. So now the image is only 150 by 150. So we've done exactly the same as last time, except now we've only kept 1 in 4 instead of 1 in 2. Okay, to reconstruct it, we've put the zeros between those. So we could have stored that, and if we want to reconstruct it and look at it, we put the zeros in, and that's what you see. And then we need to filter this, and this would be our reconstructed image. Now we see more artifacts because, yes, we've thrown away more information. Let's look at that in the frequency domain to understand what's happening. And again, here's the transform of the image. That's the same. Now our Fourier transform of our sampled image is only 150 by 150. So now we're chopping out more. We've got more copies, and these copies are closer to each other now, which means we're getting closer to a situation where we're going to have aliasing. So again, aliasing, if you don't understand aliasing, we've got a video on aliasing on the channel in the link below in the 1D case. But aliasing in the 2D case is, I think, sort of easy to visualize. If you're now comfortable with this figure, with the copies that are happening because of sampling, then when the tails of these copies here start overlapping, then we're getting aliasing, because the tail from one is going to go into the region for the other. And when you multiply by this filter here, you're going to not only be getting the portion from the original, but you're also going to be getting the tails from the copies, and that's the aliasing that's going to be happening. So we're going to see that happen more as we step through. Okay, so let's move through to this one. So now we've got another one where we're going to be even more. Now we're only keeping 1 in 10. And this is again the reconstruction. So now we've only got 1 dot with 10 either side of it, so you hardly see an image in this case. And then we filter it and we get an even more blurry one, which is not surprising, of course, because we've only kept 1 in 10. Well, let me just show another plot graph here, just to make the link back to the one-dimensional case and see what what is happening here with the 1 in 10. The image looks tiny, so we're keeping a very small number of the original pixels. So this is fantastic from compression, but of course the reconstructed image doesn't look so great. But let's look into one-dimensional. So here I've taken one row of the image, and in the red I've plotted the actual values for that for each of those pixels in that row. In case, just for more detail, of course I'm showing here 3 colors. Here I'm only showing the sample from the red color. And if you want the code, the MATLAB code for all of this video, that's available, and you can look on our website, which is in the link below. You'll find the MATLAB code. You can run the entire video through yourself, look at the code and see more detail. But here what we're showing is the blue ones are the sample ones, 1 in 10. And I should mention here, I've normalized the image to be between -1 and 1. That's why you can see some negative and some positive. I've just normalized the image. So these samples here are the blue samples, and you can see we're keeping, the blue samples are keeping the general overall information in terms of what you would look at and you would think, okay, the low frequency parts, but we're missing all the high frequency detail. And that's exactly what happens when you do sampling. And so this is hopefully helping you to extend from the 1D knowledge that you have to the 2D knowledge. And we'll come back to that in the next image that we're going to look at. So here again, we're down now, we're only keeping 1 in 10, so our image here in this Fourier transform is only 60 by 60. We've got lots of copies, and there's aliasing happening in here, which is coming into it as well. So let's have one more step, and this one's going to be 1 in 20. And so now here we're only keeping 1 in 20. This is the reconstruction, the step with the padding, and this is the reconstructed image. Okay, now what I want to show here, so obviously this is a very blurry image, it's not surprising because you're only keeping 1 in 20. But I would like to show here what the, remember I said at the start, you could take this original, you could take the original Fourier transform of the original image and directly multiply it by the filter instead of the other approach, which was removing the rows and columns. Now, if we did that multiplication, this is what the direct image looks like. Okay, so these are 2 images. One of them is done by removing rows and columns and only storing in the image domain, and that gives us this image reconstructed. And the other way is by doing the storage in the Fourier domain and reconstructing from the inverse of that Fourier transform. And now we can see a difference really between these 2 images. We couldn't really see it before when we were not doing so much compression, but now we can see a difference. So I just want to highlight the main difference here and try to understand that. In this case here, the bottom one, we definitely have only kept the low frequency components. We didn't have any copies in our image over here on the left-hand side. And so when we applied our filter, we directly just removed, this is what we've removed by applying the filter. We're only keeping now what's in the middle. So this image here is what we've removed by applying the filter, and we're only going to keep the portion in the middle. So we really are only keeping the low frequencies. And if we do it this way, we don't have any aliasing because there aren't any other copies with their tails encroaching in that area there. So we really have a very much smoothed out image. But the image above, it does have aliasing because this is the Fourier transform here in this in figure 7. And so we definitely have the tails of some of these copies coming into that central region, which is the one that we're keeping when we do the reconstruction. So you can see there are sort of elements here of high frequencies, and high frequencies show up in images as sharp edges. And so you can see that this one has a more blocky, there are more, I mean, it's still blurry, but there are some more sharper areas compared to the one below where it's only the low frequencies that have been maintained. Okay, so let's have a look now to really try to understand a bit more about this with a more fundamental image. So here's an image here, and here's an image which I have created by, here as I'm showing this is just a more colorful version of that image. So this is here, but I'll show you why I've done it just right now. I've actually done it where I've mapped the intensities to a height. Okay, so this image, this new image that I'm going to use now, is actually 2 sinusoids, one in each direction. So a sinusoid in this direction plus a sinusoid in this direction. And if you'd like more information about this, then there's a video on the channel about two-dimensional Fourier transforms, and we look at this image in that video. So I encourage you to have a look at that video to understand more about this image. But let's just think about it for a minute. Well, it's now an image which only has these two frequency components. And so this one has five periods in the image. And so as we know from Nyquist sampling in the one-dimensional case, we really only need to sample at twice the highest frequency component. So that would mean 2 samples per period. Okay, but how many have we got in this image? Well, we've got 600 samples in 5 periods. So we've got 120 samples per period. And here's what this looks like here. So I've just taken, again, a row of the image and I've plotted that. And the red is the image and the blue are the samples. And we've got, you can see we've got lots of samples, 120 in each period of this image. So this is way oversampled. And definitely we can do compression here, and we can do, for this image, we can do compression that is totally lossless, because this image does not have high frequency components like the other one did. So let's look at this for a minute and look at a few of this. We'll step through the same process as with the other image, and we'll see what happens as we're taking fewer and fewer samples from the image. We're doing more and more compression. Okay, so let's step through those here. This is when you're keeping 1 and 2. This is the one with the zeros added in rows and columns, and that's the reconstructed when you apply this filter here. So this is exactly the same case as we did for the very first step for the photograph of the building with the flag. Okay, and let's just look in here just to see to see that we understand what's going on here or what we've got here. Maybe it's hard to see, but in the Fourier domain, because there's only a sinusoid in each of the directions, we've only got 4 delta functions in the Fourier domain. So again, to understand that more, I encourage you to go and look at that 2D Fourier transform video on the channel. Okay, so this was 1 in 2. Okay, so let's now look at what we have when we've got more aggressive, 1 in 30. So here we've compressed right down, and we know that we can compress a long way. And here's what's happening in this case. So now we do have our 2 samples in the period. We've got exactly 2 samples within each period in this case. Okay, so in this case, again, we should be able to fully reconstruct this because we have there, we're satisfying the Nyquist criterion. So let's see. You'd hardly see where those points are because you've only kept 1 in 30. So mostly it's zeros in this reconstructed padded image. But when you apply the filter, you get the original image back. No loss at all, even though there are massive numbers of copies. But because the Fourier transform, because it's low frequency and there's only these sine waves, therefore there's no tails on the Fourier transform, it's just the delta functions, so therefore there's no aliasing at this sampling rate. Okay, so let's, we've got 1 in 30, let's try another even more aggressive, let's say 1 in 50. We've got even less that we need to store, so we could do massive compression if this was our image. So if our image really did only have these low frequency components, then we could do massive compression. And it would be totally lossless, even for 1 in 50. You can see the original image is fully recovered. And again, we can see that we're starting, though, to get to the limit here, because in here you can see these delta functions are 10 apart. So from 2 up to 12, they're 10 apart in each direction. And now we're seeing our Fourier transform of our sampled image. These delta functions are right on the boundary of what we're actually storing and what we're in our samples. And if we look in the one-dimensional case here, we're only just getting 2 samples per period now when we're doing 1 in 50. Okay, so we can't probably push it much further than this. In fact, we can't. So let's try beyond 1 in 50. So we're going to violate Nyquist's criterion now, and we're not going to have that. So now we're only keeping 1 in 75. So instead of storing 600 by 600, if our image only has these low frequencies in it, then we could get as low as 1 in 50. Let's see what happens if we do 1 in 75. Then our reconstructed image looks like this. And this is aliasing. So what you can see here, it's a visual way of looking at aliasing and seeing the effect of aliasing, because this high frequency, so now here, these frequencies are higher than the sampling that we did for them. So if I look at here, you can see that now we're down to only having one sample per period. So there's only one sample in this period here. Okay, there were two in this period, but there were none in this period here. Okay, so we're not satisfying Nyquist criterion anymore, which means that the frequency is higher than the highest frequency that can be recorded by our Nyquist, by the sampling that we have done. And what the effect of that is that all we are seeing now is aliasing. And what was at this frequency now comes back at a lower frequency. So these points now are further apart in the reconstructed image. Okay, and we can see that here because if we look in this Fourier transform of our sampled image now, our spikes are now only 6 apart. So they go from 2 to 8. And what that means is they're not the original spikes. The original spikes have now appeared on the other side, outside our Fourier transform square. And these spikes that we can see here are the aliased spikes from the neighboring points. And so when we look in here, there's just so many copies in figure 7 here that the alias points have now moved outside the area covered by this filtering square in the bottom right hand, and we're getting the copies from the neighboring squares coming in, and therefore they're appearing. What was a high frequency is now appearing as a low frequency. And just probably the last thing I want to say is, well, what happened? This was the way that we were doing it, where we were compressing by removing rows and columns. Well, what if we did look now at the other way, which was by going into the frequency domain and directly applying that filter? Well, as I said before, this way is only keeping the low frequency portions. So in this case, because we're now sampling so low and our filter is so small because we've sampled at such a low rate, now when we multiply this filter on the bottom right with our image Fourier transform, the filter is smaller than the area covered by these delta functions. And therefore, we actually, if we do it that way, our recovered image is actually all 0. So in this case, there definitely is a big difference between doing the compression by, in the image domain, removing rows and columns, and then reconstructing if you wanted to have it reconstructed, or moving into the Fourier domain and applying the filter directly in the Fourier domain. In this case, of course, neither of them gets you anything like the original image back because of the aliasing, because we have sampled so low. But I just wanted to point out the effect of the two different ways of doing it, and that one of them gets aliasing and the other one actually doesn't get aliasing. And in this case, because it only had that single frequency, we were left with nothing. If there were other frequencies in our original image which were even lower than 5 periods within the size of the image, then they would be showing up here. But in this case, I only had the single frequency, which had 5 periods within the image. So hopefully this has given you a lot more insights into two-dimensional Fourier transforms and into image processing, into decimation and interpolation. And I think there's lots of things that you can gain here. Again, look at the web page, download the MATLAB code, and you'll be able to run all of these yourself and spend more time to really absorb all the information in this video. If you found the video helpful, give it a thumbs up. It helps others to find the video. And I encourage you to subscribe to the channel for more videos. And again, check out that website for other videos on the channel.